to a special event today to celebrate the World Quantum Day. As we celebrate the World Quantum Day, let's also take a moment to acknowledge the profound impact of knowledge and innovation on society. We wish to explore the fascinating world of quantum science and its huge potential to change the way we live, we learn, and interact. The word quantum seems to be sounding big, at least for me, but today we are here to absorb it in a way that's easy to understand and how it's opening doors to a whole new world of possibilities. We have the benefit of this through experts from industry. Sri Sridhar Garu has already joined. He's from TCS. And Sri Subramanyam, LV Subramanyam from IBM, also joined us. And I was supporting Dr. Nibili Reddy, who is secretary to the Quantum Technology Mission, is also here. Sir, greetings to you all from APSCHE and the vice chancellors of the universities in Andhra Pradesh. Our chief minister has a dream to establish the Quantum Valley in our new capital, Amaravati. And in this particular context, we have taken the suggestions of the DST along with APSCHE to the minor program on quantum technologies, quantum computing. Already, some initiation has been done to include this as a minor course, as a part of the curriculum review that is already on, both for the engineering as well as the conventional programs. We are trying to do this. In fact, based on the readiness of various universities to include the minor courses on quantum technologies, quantum computing, we also wish to go ahead in assessing the need for training of trainers in these particular aspects. We also see that trying to compile the professionals and experts in this area to see that the hands are strengthened for various institutions here to organize such. In fact, the curriculum that has been suggested by DST through APSCHE is also circulated all the universities. Sir, I request Dr. Anil Kumar, who is the principal and associated with organizing this quantum day, to introduce our expert members to the forum. Sir, I have another meeting. I just joined in another few minutes now. I am in the midst of an executive committee meeting going on. I request Anil to go ahead. Welcome to you all. I hope we'll have a clear understanding of what we could do, what quantum science could help us in working. Thank you very much. I'll join you.
Thank you, sir. I welcome all the vice chancellors across the state. Thanks for the person of APSCHE, Professor Madhumurthy Garu, for giving us this opportunity. With great pleasure, I also thank Dr. JBB Reddy Garu, who is scientist at DST, helping us customizing minor courses for our UG as well as PG courses, colleges, students, both professional and non-professional, in terms of quantum technologies. I would like to introduce Sridhar Garu, Sridhar Garu, for this audience. Sridhar Garu is the head Coin Academia and India Strategic Initiatives, Corporate Technology of Tata Consultancy Services. Sridhar Garu heads the Coin Academia and India Strategic Initiatives with the TCS Research under the CTO office. In this role, Sridhar leads the collaborative research with global universities, Indian academia, and work on national strategic mission programs. He is responsible for driving research, innovation, teams by collaborating with institutes through strategic programs, sponsoring research teams, and engaging about leaders. He is also responsible for participating in India's strategic mission programs and organizes necessary expertise from TCS to the missions. Prior to this role, he was heading the quantum technologies incubation where TCS successfully created the capacities. 6-qubit quantum computer in partnership with the TIFR and DRDO quantum ecosystem and founded prior to this the alliances group. His efforts focused on developing emerging technology themes such as AI, cybersecurity, IoT, and drones, UAVs, through collaboration with ecosystem partners, startups, forums, and research organizations. This work is aimed to accelerate innovation, build thought leadership, and provide strategic advances for TCS. Prior to this, he also led the technology transformation teams in automotive, telecom, railways, BFS, and public sector engagements with over 24 years of experiences. He brings a blend of technology, management skills, and interpersonal skills to bring ecosystems together and drive the emerging technology themes. He currently holds the position of Vice Chair, TSD-SI Study Group for Software and Solutions, Expert Member Post-Quantum Security Task Force, Expert Committee Member National Quantum Mission, Expert Committee Member USOF Telecom Tech Development Fund, Expert Member at AICT in Emerging Technology Themes, and India Member Quad Quantum Computing Task Force. He is an active speaker at several forums and universities and works closely with BAS, ITU, SG13 for future networks and cybersecurity. With these few words, I welcome Sri Sridhar Garu to take the floor. And sir, apart from this, all vice chancellors and deans are also connected, and principals as well as students also. We have live streaming the YouTube channel also, so that majority of the faculty as well as students can benefit out of this. With this, sir, thank you very much.
Thank you, sir. Thank you for the kind introduction. Am I audible, sir?
Yes, sir, audible.
Okay. So good afternoon, everyone. My name is Sridhar. I'm based out of Delhi. I head the Quantum Technologies Group and the Co-Innovation Network Group for TCS. So first of all, thank you for giving me this opportunity to be part of this discussion and today's session. So and the celebration that we are doing as part of the World Quantum Day. I first of all welcome all the participants to this session in celebrating the World Quantum Day. So I have a very small presentation, so which gives an overview of the technologies that are in quantum and to give you a flavor of the things that are happening in quantum across the world, and then I will cover what is happening in the country. And thank you again. I'm very happy to be part of this initiative. I'm particularly happy to be part of this state government initiative led by Honorable Chairman Dr. K. Madhumurthy Garu and the team. And I welcome you all to this session. So with me, I will go into the presentation, taking you through few slides. So let me know when you can see my screen, please. Yep. I hope my screen is visible. Kindly confirm, sir, when my screen is visible.
Yes, visible, sir, visible.
Okay, thank you so much. So the next few set of slides, I'm going to talk about the quantum technologies and how it is shaping up. That will give you a quick insight of the things that are happening. I'm sure you will not be left out. You will have up-to-date information about what is going on in the world with respect to the quantum technologies. And this acts as a very refresher course for all of you. It's not a course, but I'm certainly sure that it will give you enough information for you to have insightful discussions around quantum with anyone. I will keep this subject very non-technical. This is extremely complex topic to explain, but I will try to make sure that it is covered in as much as simple terms as possible. Okay, yeah. So first, it is marked as United Nations has marked 2025 as a year of quantum science and technology. So it is mainly to mark the celebration of 100 years of quantum mechanics. So which means quantum is not a new subject, it is pretty old subject, but there are a lot of developments that happened over the last decade. But given the things that are happening globally, so this year United Nations has announced this as International Year of Quantum Science and Technology. The goal and mission of this initiative is to promote and spread awareness about around quantum to all parts of the world, and then help people to understand this great technology that is coming. So with this, I'll move into the agenda for today. So it is structured something like this. I'll just give a quick introduction of quantum, and then we'll jump on to the things of why this technology is important now and what is happening inside quantum machines, and then how it is used for solving computing problems, and what are the implications on security, sensing, etc., and give you some overview about National Quantum Mission. I think you can absorb all the content in a very relaxed way. Gives you all critical information that is required for you to have conversations meaningfully with your students and or other expert members. Okay, so the topic itself is little tricky to explain. So, the quantum mechanics is always an intriguing topic, but one of the simple way of imagining this one is the power of gods, right? So all our Hindu mythology gods have got multiple hands, multiple heads, even the Rakshasas have multiple heads and all these things. Now imagine the scenario where you have this power to move these hands in unison and then do multiple activities. So each of the hands can work together to arrive at a task. So which means you naturally get a lot of speed, and your ability to complete the tasks is amazing, right? So this phenomenon actually generates humongous amount of power to compute the tasks or complete the tasks. And if you apply multiple brains, right, you also have multiple heads, and then you operate 2 or 3 hands in unison, and then control 2, 3 phenomenon in these things, then you can actually do a lot of interesting mathematical problems, right? So this has been in mythology, but translating this into the current world. So in our classical computing world, what we are seeing today is having bits. So these are called binary bits, which are either zeros or ones. So whereas in the new world of quantum, so it leverages the principles of quantum mechanics, so which is based on the behavior of atomic and subatomic particles. And here we have something called qubits. So where this qubit can also be not just 0 or 1, it can exist anywhere between 0 and 1 simultaneously. So it has got some interesting principles of quantum mechanics. I will not go into the details just to avoid the complexities here, but 3 important principles that actually help us to get quantum phenomenon into effect, and that will be leveraged for solving multiple things, be it in computing, sensing, or security. So the first principle is called superposition, where these bits not only exist as 0 or 1, but can all simultaneously exist in 0 and 1 state. The second phenomenon is entanglement, where multiple qubits can be tied up together, and if any change that is happening on first bit also impacts the second bit, even irrespective of the distance they are separated and there is no connection, right? So that phenomenon is called entanglement, and this phenomenon is harnessed to do some amazing things. And the third phenomenon is interference. So where these qubits, when they are interacting with each other, generates different energy levels, and these energy levels are used to solve mathematical problems. So these are the 3 phenomena that are used in harnessing them and generating that into computing. So which creates massive parallelism. So it will be easy for us to identify the global minimum and maximum scenarios. It will provide quadratic or exponential speedups. I'll just come to that, what it means. And then it also creates a lot of energy efficient. So to keep it in a simple terms, so we are now using atomic and subatomic particles to do the computing, so which is much more powerful than the classical computing. So quantum computing will not be a complete new thing. It will not exist in isolation. It will work alongside of a classical computer, and it takes a small problem and then it takes a problem that cannot be solved with a classical computer and then solved with a quantum computer. So we will come to that, what problems these are. Right? So quantum computing has many applications. So today, so all the problems that we categorize them as NP hard when we are doing our optimization, we classify some of the problems as NP hard, the problems that cannot be solved in non-deterministic polynomial amount of time. So just adding one variable increases the complexity of the problem, and that cannot be solved in polynomial amount of time. So these problems are solved on quantum, but it has also got the limitation. It will not solve the simple problems. So it is not useful for solving simple problems. For example, if you say 2 plus 3, so on a classical computer, it is deterministically 5, whereas in quantum computer, it may be 5. So quantum computer is probabilistic in nature. So this phenomenon can be used effectively, because when probabilities is applied on large samples, gives best results. So that phenomenon is used in computing. So we can use this phenomenon to solve problems in supply chain optimization, crew scheduling, dynamic scheduling of workforce, drug discovery, a lot of problems in finance, financial risk management, insurance, etc. So there are plenty of applications that are possible. So huge list of applications across all verticals that are listed, and there is also a national call that is going to come up on quantum algorithms, so where people can try to solve these problems. Okay, so this is fine. So now we understand atomic particles are being used to do these calculations, but how are these things looking like, right? So these are some of the examples of quantum machines that are available today. So IBM is the pioneer in this space. So they uses a phenomenon called superconducting qubits. It's got the best quantum computer that is available today, also expected to come to Andhra so soon. Uh, we have other computers like D-Wave, which is called an annealer, which is useful for solving certain kind of problems. Then we have Google's superconducting based qubit quantum machine. Then we have Rigetti, IonQ, and many other companies that are actually working on quantum computers today. So there's a terminology called annealers or universal quantum computers. So annealers are systems or quantum systems that can solve a part of or a kind of a problem statement. Like for example, this D-Wave, the machine that you see here, is called annealer, which solves optimization problems very effectively. And universal quantum computer is something that can solve any problem, any mathematical advanced complex problem. So these are still in evolution, so they're getting better and better every year. So quantum computers follow something called Rose's law, where the quantum volume or the number of qubits double every year. So in the previous slide, we talked about generating quadratic speedups or exponential speedups. So what are these quadratic or exponential speedups? A quadratic speedup is something, a problem that takes million steps to solve on a quantum computer. So we'll take square root of million, which is 1,000 steps to solve the problem. So this is what we can do with quantum computer by applying these principles of superposition and entanglement. The other way of solving problems, or other thing that is also possible with quantum computer, a problem that takes 2 power t times to solve on a classical computer can be solved in t times on quantum computer. So these are the reasons why there's a lot of emphasis on quantum computing. So if you have this kind of power that is available, we can solve most of the complex problems that are there in the world today. So we also don't know many complex problems that are beyond our imagination, but the problems can be solved at either quadratic and exponential speedups. We'll come to that in the coming slides a little bit more in details, what type of problems people are solving. Okay, so how are these quantum effects generated? So the quantum effects in this slide, I talked about IBM generating quantum effect through the supercomputing qubits, but there are also other technologies in which you can generate these quantum effects. So today people are working on different technology groups, technology themes. So there are players who are working on superconducting based qubits. There are also companies that are working on trapped ions, where they trap ions to generate these quantum effects. And there are people who are using optics, using photonics to generate quantum effects. And similarly, recently we have seen announcement from Microsoft, which uses a topological qubits based approach for generating the quantum effects. So there are multiple ways in which you can actually generate quantum effects. But uh, uh, yeah, today superconducting is actually leading the race, but we don't know how the things will evolve in future. So in general, so all the companies are right now working on different methods of generating quantum capabilities, and a lot of countries are actually racing to make investments into these technologies. And these technologies are also extremely useful for many other things, not just the quantum computers. For example, quantum dots is a technology that gets into our TVs. So similarly, photonics is something that is used in communications. So there's also a lot of adjacency technologies that gets benefited by the developments that are happening in quantum. So we will deep dive a little bit more to understand how these systems look like. So this is an example of an IBM quantum lab. So where you can see a quantum machine, quantum computer. So there is a quantum processor here at the bottom of the hand. Here you can see the quantum processor at the bottom, and then it has got a chandelier kind of circuitry, so which is nothing but it is a cryogenic system which actually reduces the temperature as you go up, and this entire thing goes inside a chamber like this. And then the entire thing is controlled by electronics control circuitry, so which will enable you to measure the qubits, and that will help you to solve the mathematical problem. So today you provide software interfaces that run on this control system. So you first take a mathematical problem, translate that into quantum domain, and then run it on this quantum computer, and then do the measurements, and that measurements provides the solutions to these things in a simple way. But this is a example of a quantum system. But depending on the technology in which these quantum bits are generated, so your system might look completely different. So this is an example of a superconducting based qubit system. Whereas if you see another company called Pascal, so they use something called neutral atom based technology. So their systems look completely different. Right. So we'll not go much into the details. Today we have IBM, which is leading it with 156 qubit machine, and Google has got 105 qubits. There was a recent announcement from Google. Companies like Rigetti, they're at 81, IonQ at 35, and Pascal about 200 qubits of neutral atom kind of things, etc. So, and D-Wave has got 5,000 plus qubits, but it's called an annealer, so it can only do certain kind of problems. So typically, so what we can do, if you have about 40 qubits, so you can solve a 40 asset portfolio problem with Markowitz model. So Markowitz model is a Nobel Prize winning model that is used in portfolio optimization for optimizing risk and return scenarios. And it is a NP hard problem, and you have to do continuous calculation of the covariance matrices. So you can build a 40 asset portfolio with 40 qubits if you have 40 qubits. If you have about 450 qubits, you can solve problems like carbon capture, technologies that will help us to fight the climate change. If you have 1,000 plus qubits, so we can solve many problems in pharmaceutical industry, and we are all hoping for getting to 1,000 qubits. That's when we will see the commercial advantage. So this will significantly reduce the development time of vaccine. So because you need to do a lot of simulations during your pre-drug design process, you have to identify the target molecules by doing these simulations, and that's when the quantum computer helps. And this is actually being experimented by all leading players across the world. So there is an alliance called Pistoia Alliance, in which there are top 17 pharma companies are part of it, and all of them are working on it and sharing knowledge. All big pharma brands across the world are working on quantum computing today. Okay, so let's take a look at what are the developments that are happening globally, so that we understand why it is important now and why last decade has been little significantly important, and why this has been developing very well. So quantum ranked at number 5 in terms of number of patents applied in the last 3-4 years. So there's a good amount of patents that are coming from big players like Honeywell, IBM, Microsoft, Samsung. All these companies are applying patents in quantum. The VC funding is also very vibrant. So this is 2022 data, 23-24 data is also very vibrant. It's about more than $1 billion of investments that are coming into into the quantum technologies, and these startups are also listed on the New York Stock Exchange. We have IBM quantum machine, which is 156 qubit device. IBM had also launched a 1121 qubit device, but this has got qubits of different quality, and now we have much more powerful quantity of devices that IBM had launched. 24 countries have got quantum as a national program, so you can imagine the amount of funding that is getting into it. So more than $50 billion of investments are coming into quantum. So there were also a lot of Nobel Prizes in this in quantum technologies over the last few years. I think last 3 years we have seen prizes in physics and chemistry getting into quantum technologies. And apart from this, there's a lot of regional alliance activities that are happening. So every country strategically bringing all the stakeholders together and then creating alliances to build this technology. So something called QFarm, which is from Pistoia Alliance, QSTAR in Japan, and QTAC in Germany, QEDC in the US. All these are a lot of regional activities going on, and many companies are coming together and collaborating on this technology. So the technology is expected to give significant amount of jobs and create good amount of value in the coming years. Again, so India has also invested into this technology with a 6,000 crore funding. We joined along the sides of UK, Japan, China, US, and all these countries have invested significant amounts into this technology. So inside superconducting quantum computer, so it is not difficult to understand. It is simple to create. So I'll give you two cases of India initiatives that are going on. This is the first example where TCS has partnered with TIFR and DRDO. So where Professor Dr. Vijay Raghavan was creating the 6-qubit quantum machine. TCS provided the software interfaces for this one. So we provide the software and simulator for running running programming on this quantum computer. So this is his lab, which is in TIFR Bombay. This is another example of another quantum computer, so produced by an Indian startup. It's called QPi AI. So they are working towards 25 qubit quantum machine. So they've already built a lower version of quantum machine. So again, if you look at the parts, these are all superconducting based qubits. So you have a cryogenic refrigerator, which generates sub-zero temperatures, and inside this there is a quantum processor. So the quantum effects are produced only at sub-zero temperatures, and the quantum processor is basically an indium is a semiconductor that is generating this generating the quantum effect, the superconducting effect, and then these are controlled by a control system, a good amount of control electronics. And now the software interfaces are fully standardized. What it means is, even if this quantum computer is not accessible to us, we can actually start working on simulators, or we can have an interface to this quantum computer through remote, and then hook onto these quantum computers and run our programs, run our algorithms on this quantum machine. So today, all major quantum computers that I spoke about produce cloud-based quantum services through Amazon, Microsoft, and AWS. So you can just get onto AWS quantum computer or IBM Cloud or Azure Cloud, and then access these machines and then try your programs. Not only that, you can actually take the simulator, the Qiskit simulator, and run it on your own laptop. You can run up to 22 qubits of programs, and beyond that you will face some issues, but if you have powerful machine, you can go up to 30, 34 kind of qubits. But beyond certain number, the classical computer can never match quantum computer, and that's the power, right? And that's where the quantum computer has an edge, and then you'll be able to solve bigger size problems, extremely complex problems on quantum computer, which you cannot even imagine to solve on classical computer. Okay, so moving on, so we'll just try to understand what kind of problems that people are solving today. So I'll give you a few examples so that you know what people are doing. So the first one is an example of the traveling salesman, which is very common problem statement. So which is, imagine you are trying to build a optimized route between different cities. So this is a NP hard problem because if you have to create an optimal route plan for 10 cities. It is about 362,000 combinations. But if you add one city to it, it becomes 3.5 million combination. And if you add another one more city, it becomes 39 million combinations. So every city that you add, the problem scales exponentially. And this is what we are saying, these problems cannot be solved with polynomial amount of time. So, but these problems can be solved linearly or in polynomial amount of time using quantum machines. So this is one of the best problems. Now imagine the problem of an Amazon delivery, which is a combinatorial optimization problem, right? So where Amazon has to choose the size of the truck, the address, and the time at which the customer wants the delivery and the route it has to follow. It is a combination of 4-5 optimization problems that are brought together, and then you try to solve the problem. And this is very difficult to solve on classical computers. So typically we try to fix some of the things and then do heuristics around it and then try to solve the problem. So these are problems good for quantum machines. So the expectation is we take these kind of problems and model them on quantum computer and then try to solve these problems. This is one of the examples. Another example which is very popular is actually happening in the chemistry and pharma domain. So you can do a lot of simulations in pharma domain or the chemistry domain using quantum computers. Today people are actually doing quantum inspired simulations also on the classical computers. Even that is also showing good amount of promise. So this is an example that IBM had published. So this is an example of a caffeine molecule. So to solve this simulation of this caffeine molecule, to measure these ground state energies of these atoms that are linked, so you would require about 160 qubits to model this problem. If you have to try this problem on a classical computer, so you will require about 10 power 48 bits. And if you put all the computing together in the world, so which is around 10 power 20, so you will not be able to solve the problem by putting all the computers together. So, but if you transfer this problem onto a quantum domain, you can solve this problem with 160 qubits. And today we are talking about having very good 156 qubits. So this problem is close to solving the simulations of a caffeine molecule is possible. So this is an example of an example of a simulation problem that can be solved using a quantum computer. But the expectation is if you have 1000 qubits, so then we'll be able to solve uh, the small atom kind of problems at a scale that is useful for commercial level. So all pharma companies are working on these things. So you can imagine the same is applicable for materials. So there's a lot of material companies that are also working on quantum technologies. Right now it is all the experimentation phase. People are trying to understand the methods and mathematics behind this one to understand quantum technologies. Another example is say grid optimization problem. So which is where you have distributed energy resources. Today we see a scenario where we have power coming from different solar panels, we have battery storage systems, we have microgrids, we have the biogas plants and the conventional thermal, hydro and other forms of energy that is coming. So in order to model this properly and then provide say optimized analytics to the national load dispatch center. So this, when you model this problem, when customer becomes prosumer by adding a solar panel, so the problem becomes very difficult to model. So you need to have a large size quantum computer. So today again we use heuristics or solve the problem in parts. So we cannot solve this problem as a whole. So this is another problem for a quantum machine, and there are large companies like the French major companies and the US major energy companies are working on quantum machines to solve these problems. So I'm also giving some examples of what TCS is working on. So we've been working on multiple problem statements, so which are in the states of optimization, machine learning, simulations, etc. So these are the things that we're working on. In summary, actually, what kind of problems if you can solve on quantum machine is anything that is AI ML. So whatever AI that we are talking today, those problems can be solved with much more speed ups. You can actually transfer a part of the problem to quantum computer and solve it at speed. So you can imagine a network like UNet. So if you are working on image processing, you will know this image segmentation framework called UNet. So you can actually solve the part of the problem on quantum computer and then take the results and then combine that with classical computers. Similarly, you can solve optimization problems in finance domain, optimization in logistics and workforce scheduling, etc., route optimization, things like that. Then you can also solve the simulation problems, which are like Monte Carlo simulations or any financial risk simulations, etc. So those are the other kind of problems that can be solved. So a lot of statements are now coming. So people are finding innovative algorithms. Okay. I just want to give a flavor of what is happening around the world. So around the world, these are some of the major brands that are working on quantum today. So it is not new. So we have to adapt ourselves quickly and then understand this technology and then see, because it's also going to create another software kind of revolution. So we'll have to understand this quickly and then combine this our existing knowledge of AI, machine learning and other things, and then add quantum knowledge also to this and lead this technology area. So all the major brands have started working on quantum. So specifically, I have some examples also here. So like, for example, what Coke has done is, so they were trying to optimize their the kiosk machines, the vending machines. So there are about 700,000 of these machines in Japan, and they're trying to find an optimum route for servicing these things. Nestle is doing a very interesting thing. It is trying to solve the thermodynamics problems. These are thermodynamic models that will help you to model the consistency of food and taste. So these are problems that are difficult to solve on classical machines. So they're trying to attempt with quantum. Enel Energy, which is trying to do the optimal travel routes for the maintenance of their distributed energy resources. So this is again a workforce scheduling problem and route optimization problem. So plenty of examples are available. So and Roche here, they're working on a drug discovery problem statement. So this is for Alzheimer's disease. They're working, they partnered with UK-based quantum computing, Cambridge Quantum Computing, which is another popular company in this space. So they're working on this problem statement. So these are some of the examples on the computing side. So just to summarize, so any problem in AI ML can be solved at quadratic or exponential speedups. An optimization problem can be solved, and simulations you can solve them with an exponential speedup. So these are some of the things. This is the power that you're going to get. So now imagine this technology goes to the adversaries and falls in the hands of people who want to abuse this technology. Right. So there are risks that are going to also come with quantum. So now we are saying that we have enormous amount of power, so we can solve any amount of mathematical problems. Now imagine the scenario of our encryption algorithms. These are all solved with mathematics, right? So our RSA algorithm or AES algorithms are based on mathematics. So now the question naturally comes, if we have a reasonably powerful quantum computer, can we break these algorithms? And the answer is yes, or because these are based on mathematics, so we can find methods to break these algorithms. So we have to do something. So there are also people who are hoping that, yeah, in future, a powerful quantum computer will anyway break these algorithms. So they're harvesting the data now to decrypt later. So this is called harvest now and decrypt later kind of attacks. So where you take all the data stored now and wait for the future algorithms to break these things. While these algorithms are complex, these are designed to take thousands of years to break, but with quantum computer, so let's say it's not one quantum computer, it is a network of quantum computers that you use to solve these algorithms. So it can probably break these algorithms in minutes. So people have given different numbers. So number of qubits required to break a quantum machine, break a quantum algorithm, quantum encryption algorithm examples, right? So there are two popular algorithms that were there. So people have demonstrated that using Shor's algorithm, you can do the prime factorization. So this will help you to break that RSA encryption algorithm. So which means we are at risk wherever we are using these RSA algorithms. And similarly, there is another Grover's algorithm, so which is used in search. So this provides exponential speed up to search using the quantum methods. So using these algorithms, so there's a chance that we'll be able to break these quantum machines, quantum encryption algorithms. So there's a survey that is done every year by Global Risk Management Institute. So people feel that, yeah, this is coming and we have to do something about it. We have to protect our future encryption things. Otherwise, our secrets are all be broken in 10 years from now, and that is a serious risk. So, but the good news is NIST has already started a competition around this one, and they started shortlisting algorithms which are resistant to quantum attacks. So even if you have a quantum machine, so you'll not be able to solve those problems. So we have some new standards that NIST had launched in August of 2024. So there are 3 standards that were there. There were 2 new standards that were announced recently. So there are 5 algorithms that are available now, which you can use. These are encryption schemes that you can use. India is also putting our own efforts in terms of launching India-based algorithms. And we have some good scientists who have actually published in this NIST standards. So one of the professors, his algorithm is actually used by Korean government, and they published a national standard around that algorithm, which is inspired from a professor from India. So India also at PQC, so this is called post-quantum cryptography. So we're doing a lot of activities around building these algorithms and then promoting migration into this new post-quantum cryptographic schemes. So once we have these algorithms, so we have to change our existing encryption schemes onto these new schemes so that we get protection from quantum computers. But how quickly we have to do is all a question of discussion, and that is where a lot of opportunity is going to be generated. In US, government has already given an order. So in Singapore, Germany, UK, there were guidelines that all the people should be ready for this quantum attacks, and then you have to do this migration into the new encryption schemes. So US has given a very strict guideline on this migration roadmap. So, and because of this one, so a lot of banks have already started exploring, okay, so if there is a quantum computer, so how will we protect our data? So there's a lot of action that has already started at banks. As TCS, we are also partnering with few banks and working on this specific area for the quantum security. So there's a lot of opportunity in this space. So anybody who is working in quantum security space can think of post-quantum cryptographic algorithms, their migration strategies, and how do we protect our current web or public key infrastructure. How do we protect that from quantum is something that we need to think of. Just quickly move fast a little bit. So there's also a second foolproof method. If we harness these quantum technologies well, we can also create more powerful networks which are much more secure. So here, this is a quantum key distribution switch, which uses quantum keys. So this quantum key is based on principles of quantum mechanics again. So if anybody tries to tamper data coming out of this switch, so you will be able to identify that there is a tampering of data. So today we don't have that feature. So if somebody taps our data in the network, so we don't know. But soon we are going to have this capability using these quantum key distribution switches. So that gives us the ability to detect the tapping of networks. So this is going to be a much more powerful feature, and countries are actually working towards building their own internet technologies using these switches. So in India, a few companies are working on it. The startup by name QNU Labs, it's a government organization, CDOT. They have already built these quantum encrypted switches or quantum key distribution switches that they have built and can be used for short distance communications. Long distance communication is still a challenge, and that is what is the problem being solved in National Quantum Mission. And the problem can also be extended to space. So today we have satellite-based QKD, where they have already demonstrated this distributing the keys using satellites. So India has also done some experimental demonstrations. So it is possible to distribute these quantum keys over free space, and these keys are extremely secure. And if anybody tries to disturb the key, so you will know. So that's why the key is safe, and then based on that you can make changes to your data encryption scheme. So this is another technology theme that is evolving. So in security part, there are 2 themes. The first one is about protecting. So the first one is about attacks from quantum computers. So what we call it here as PQC, or quantum safe cryptography. So where we are trying to move to new classical cryptographic algorithms which will protect us from quantum computers. The second part is quantum key distribution, where we are generating keys using quantum methods. So, and that is useful for us to build more secure communications. So you must have heard about Russia building their own internet, China building their own internet. Even we have our own internet in India as well. So the thing is, these kind of switches will give more ability to secure it and detect attacks outside. So the next topic is sensing. So a lot of interesting things are happening in this space. This is also considered to be the near-term technology with quantum sensing. So quantum sensing has been there because the MRI machine that we use uses superconducting based technology, which is already used for mapping of our brain images. So here what we are now doing is we are moving towards a miniaturization of the technology. So this is a picture from University of Nottingham. They are building a small quantum sensor that goes into this helmet. So there are a bunch of sensors that goes into this helmet and does exactly what an MRI machine does. So in quantum, so gives one more ability to do these measurements at more precision and better accuracies than the conventional technologies. So multiple of these sensing methods are going to be changed in future. So we have better precision fields. So instead of doing at nanotesla, we can do at femtotesla, attotesla kind of ranges. So because we can measure magnetic field, we can also do electric measurements with much more precision. So we have time, so the atomic clocks will have much more precision with quantum technologies. We have gravity meters that people are building, so which has got even better sensitivities than the current gravity meters, so which will give us the ability to map the Earth's surface. And this is a couple of things are being done at ICER Pune and National Physical Laboratories. So they're building the gravity meters. IIT Bombay is building the magnetic field measurement device, in which TCS is also a partner. And then there are also inventions or innovations happening around acceleration or GPS denied inference meters or gyroscopes that are used. Like you can imagine right now, the GPS is completely jammed or attacked very frequently by adversaries. So the recent one, even the flight that went to Myanmar for rehabilitation, so even that got attacked by GPS jammers. So those things, we don't need GPS in future technically. So with these quantum sensors, so we are moving towards that kind of technologies. And this particular technology is already demonstrated in the UK, and they have already tested this in one of the aircrafts. So this is another interesting. It is complex to build these sensors. First is to produce these quantum effects, and then using those quantum effects to do these precision-based measurements. So is critical. So you have all these things are changing. So you have better atomic clocks, better magnetometers, electrometer, and gravimetries are things that are coming as a part of the quantum sensing technologies. And this is an example of one of the labs at IIT Bombay. So this is the quantum diamond microscope. So TCS is a partner to this project with Professor Kasturi Saha from IIT Bombay. So she has built this lab and building a very compact magnetometer. And this can be used for inspection of, say, a semiconductor chip, or it can be used for monitoring the neural activities of the brain. So this is an example of a quantum microscope, so which detects magnetometer, which can do magnetometry at very, very high sensitivity level in the range of femtotesla range. So we talked about three different areas. So one on quantum computing, second on quantum security or communications, and the third one is quantum sensing. So I will briefly cover about the National Quantum Mission and things that are happening in India, so that you get a flavor of what is happening in India. So luckily in this technology, we are actually doing very well. And the mission is spearheaded by Dr. JPV Reddy and taking shape nicely. So the call for proposals had come last year. So this is a 6,000 crore initiative for 8 years. So in the areas of quantum computing, quantum communication, quantum sensing, and metrology, we did not talk about materials and devices, but these are the components that actually go into building all these three things, and also many more other things like semiconductors, etc. Right. So the mission has got specific objectives in terms of building 1,000-qubit quantum computer for the country, and then build the satellite-based QKD communication for about 2,000 kilometers, develop a intercity quantum network, and develop quantum memory and entanglement technologies that will help us to use this network at scale, then build quantum magnetometers, atomic clocks, and quantum sensors as a part of the sensing theme, and finally the materials, building novel semiconductors and superconductors and other materials we used in building this quantum technologies. So these are the 4 different themes under this National Quantum Mission. So the call went on last year, and then finally the 4 thematic hubs were announced. So it is a consortium of university kind of project. So where a group of universities came together and then started solving on the problems in these areas. So the 4 thematic hubs, India has announced 4 thematic hubs in last year, September. These 4 hubs are IIT Madras for communications and security, IIT Bombay for sensing, IISc Bangalore for quantum computing, and IIT Delhi for quantum materials. And about 150 plus organizations are part of this initiative in the country. So from Andhra Pradesh, IIT Tirupati and IISER Tirupati are involved in these initiatives. But there's a lot of vibrancy. So individually teams were working before, but because of the National Quantum Mission, so people started collaborating and then started working on this technology theme. Then subsequently, there was also a call for startups, funding for startups. So there were about 8 startups that were funded by Department of Science and Technology. So they have given funding to 8 startups working in different technology areas, in security, computing, sensing, and these are very interesting startups from the country, and they're doing very good work. So the funding was also very generous, in the range of 10 plus crores to all these startups, and actually even bigger funding. And these startups were now uplifted with fresh round of funds by Government of India, and they are building these technologies. So on the first part, so we have these T hubs, which are funded, the thematic hubs that are funded by Government of India under the National Mission for National Quantum Mission. And then in the second round, they've given startups, and then now there's another call that is going to come for quantum algorithms, and again another round of funding that is going to come for startups. So which means a lot of investment that Government of India is doing into this initiative. Now the enterprise participation is not very much right now, but because the technology is moving from experimental to real, so it is becoming better. So companies like TCS, Wipro, Infosys, Accenture, Capgemini are all working on quantum technologies with small teams right now. Okay, so this is on updates from the National Quantum Mission, but I think you keep watching out this space. There's a lot of opportunities that are going to develop in this area. And coming to Andhra Pradesh, so a recent initiative that was started last month, so which is a national is a AP Quantum Valley. So there was a first discussion that happened around setting up of a quantum valley in Amaravati. So TCS, IBM, L&T are part of this initiative. So this is shaping up. So we'll keep you posted as it shapes up. So this is the vision of our Honorable Chief Minister Nara Chandrababu Naidu Garu has taken this initiative, and we are providing all the required support for bringing up this into the state. So, I think the environment is becoming very vibrant. But so just to understand the things that are going to happen, so the technology is going to see an inflection in the coming days. This is the roadmap that we generally use to our customers. But to simplify this, I will only tell that we have actually built a real we are at kind of very close to the inflection point that is going to come soon. So IBM and Google had published a 1,000,000 qubit roadmap for 2029 or 2033. But the way the engineering is happening, so it is going to be very near. So it's time that we all invest into this technology. And the beauty of this technology is it is a multidisciplinary engineering, and it affects or it impacts all branches of engineering. So it's not just a computer science game or an electronics game. It is actually, you have to build good cryogenic systems. You have to build very, very stable environments for measuring these quantum qubits. You have to build new materials. So it's actually an amazing combination of engineering disciplines that are coming together in building this technology. So you can also imagine the semiconductor technology that is also shaping up very well. So we are right now seeing processors that are coming at 2 nanometers. So eventually we'll go at 1.4 nanometer by 2029 as per Intel's roadmap. But beyond that, we are actually getting into the subatomic uh, nanometer technologies only, which are atomic distances, 1 Angstrom kind of distances. So which means, so beyond some nanometer, so you cannot scale these semiconductors beyond a point, and then these quantum plus semiconductors work together, or quantum plus photonics work together to create amazing new technologies. So this is the roadmap. So just taking a stack view, so means some people look this from software perspective. So we need not spend much time on the hardware part here. So we can only focus on upper layers and solve the software. So this is the software representation, and we say TCS plays here without buying a quantum computer. Or we can say I will use the quantum computer that is coming from IBM or anybody. They make the quantum computer, and I work on the software part of it, writing algorithms and solving the problems. So this is something that we can do today. India is the largest community of software developers. So you can actually get onto this and then work on this one. And from the India perspective, I think we'll see a lot of this products and solutions, algorithms and simulators. These are things that will come, and there will be also opportunity to play at the hardware layer. While we're making these 1,000-qubit machines, we invent and discover many more new technologies that will help us to this. So with that, I'll just come to the last slide. So what are the key takeaways of this area, this technology area? So the first thing is it is a multidisciplinary thing, and it addresses all branches of engineering. And imagine you have to make a superconducting qubit. So you actually require help of a cryogenics engineer who can make a biggest cryogenic cooler. So suppose I have to make 1,000 qubits machine. So I have to create a processor that harnesses all the wires, and all these things can be uh, put into an enclosure or a huge cryogenic machine. So that is impacting all branches of engineering. So yeah, so I think that's the most important point, and this has got a lot of adjacencies to all other technologies like what we learned today. So I talked about AI/ML problems being solved, which means you should know AI. We are also solving this security problems, which means we also know security. So we're talking about materials and semiconductors for sensors. So these are again new materials that will help us to solve sensors problems. But those sensors engineering is again common electronics right now. So it's combination of skills that would be required. So there's opportunity for everyone and every branch of engineering. So this time we encourage all our future generation to look into this technology area. One important area that is shaping up is the drug discovery and optimization, or drug discovery area. So this is, I think we should give some emphasis around this one for solving the algorithms. So in India, on the software side, we don't get into this sciences aspects, but these are things that we can do with quantum, which is possible to imagine with quantum. So we should enable our people to think about battery materials and new catalysts, etc. And some of these unsolved problems like drug for malaria and sickle cell disease. So these are also problems that we can deal with using quantum computers. So this is uh, the technology of the future that is coming to all of us, and we're lucky to be in a state that has taken some steps towards bringing this technology to the people. So I hope it will be a great future, and from the industry point of view, we will support in whatever way possible to scale up this technology. Not covered on the what TCS is doing. We've been working on this technology for about 7 years, working on all aspects of quantum computing, quantum security, and quantum sensing. So these are the 3 areas where we are working, and we have teams that are working with our customers in solving these problems. We also take a lot of interns. This is itself is a new technology area, so I have taken interns from say ISO Tirupati. I've taken few interns there in the past, working for me on quantum security problems. So yeah, I think there's a lot of play. Industry and academia can work together in shaping up this technology. With that, I'll take a pause and thank you for giving me the opportunity to present this. And I hope I've given a decent dump of what's happening with this technology. And if you have, I'm sure there will be a lot of questions. This is a heavy topic. I'll be happy to work with you or assist you in if you have any questions. With that, I'll take a pause. Thank you so much, and I'll end my presentation.
Sir, on behalf of APSCHE, we profusely thank you, sir, for wonderful presentation. Really to learn many things. Maybe many universities and higher educations will benefit from you. And one request from APSCHE, sir, as we are going to begin short-term internships, I think as TCS is also providing, we may approach you, sir, for this short-term internships also.
Sure, sir.
Now I request our chairman, sir, to interact.
Sir, you are on mute. Please check once.
Am I audible, Andy?
Yes, sir.
Audible, sir. You are audible, sir. So once again, you gone to mute,
Once
sir.
again,
Please check once. Some problem with the connectivity.
Meanwhile, can I ask one question, sir?
yes, sir.
I am Professor Sudarshan Rao, sir, Vice Chancellor, JNTU Anantapur. So you were saying this quantum has got multidisciplinary applications in different branches of engineering. So can you cite a few broad areas in civil and mechanical engineering to make them more popular among the students now, sir, where quantum we can take it to the curriculum?
Sure, sir. So here we're talking about two sensors, the gravity meter and the magnetometer. So the gravity meter is used to do these gravity measurements, and the magnetometer for the measurements of magnetic field around the Earth. So people are trying to build these geo maps around these magnetometers and gravity meters just to understand the subsurface phenomenon, because these are very sensitive. So you can actually understand the subsurface activity based on this one. So in fact, I think there are companies that are working, like for example, there's a company from France that is working on this gravity meter for defense purposes, so where they try to monitor this subsurface analysis based on these gravity meters. Similarly, the magnetometer data is used for prospective modeling, so which is mainly the mineral exploration area. So that is also the prospective maps are built. The prospective modeling is also expected to provide GPS denied or the maps that can be navigated without GPS environments. So these are some of the applications for the civil and mechanical engineering. Particularly for mechanical engineering, there are a lot of things that are possible. So here all these new materials, the computational materials engineering is entirely, so today it is a high compute area, heavy compute area. So that can be transformed using quantum. So you can use quantum based approaches for solving or inventing these new materials. So that is one. Second is the building of these quantum machines itself is an engineering by itself. So we need skills in precision engineering, building these these cryogenic instruments. So we have, I can give an example, right? There's a startup that has built a very nice laser, but he has to package it very nicely. So it requires, again, aspects of mechanical engineering to get it right with very high precision. So these are some of the examples where the mechanical engineering teams can contribute. Like today,
Yeah. Can we develop these quantum sensors for subsurface water table identification
yes,
and earthquake possibilities? Can we develop, sir?
yes, sir, that is possible. Yep.
Okay, sir. Thank you. Thank you.
So ICER Pune can help sir on this one. So they have a demonstrable gravity meter that is available
Okay.
with them, and magnetometers. I think Professor Kasturi Saha from IIT Bombay, so they can help in sharing the knowledge around the use cases.
Sure, sir. Thank you, sir. Thank you.
Thank you, sir.
Thank you, sir. Any other queries, sir? Any other?
Sir, I am Professor Narasimha from SU University Tirupati, sir, Dean R&D. Can you explain some of the important applications of quantum in medicine, like quantum dots for the detection of tumors in brain, sir? And one more thing you mentioned about the drugs for sickle cell anemia. Sickle cell anemia is a genetic disease. So how can we develop the drugs for this hereditary diseases, hereditary diseases?
So, sir, this is the first part of this drug discovery value chain has got a lot of software-based simulations. So, so today any drug that is built by these major companies, Pfizer or BMS or whoever. So the first part to identify the target, they do a lot of simulation studies. So people have now migrated to using AI and ML or even Gen AI now to do that first part of target identification, right? So the target identification would require these simulation studies where you can do with much more precision. Right? So for example, if you have to calculate this bond energy states with more precision. So today it is estimation. So you will now have the ability to do with more precision. So once you do that, so your identification of a particular drug target is high. The probability will be high. So that will help you to do this fast and do this more precisely, more accurately. So is what everybody is trying right now, sir. So with sickle cell, so let's say you have 1,000 atom drug target that is available to attack this disease. So whether it is genetic disease or non-genetic disease, but you are trying to shortlist candidates for these drug targets, you need to study the impact of this drug against that disease. All right. So to do that studies, so the scientists in say, let's say a scientist in a CSIR based chemistry lab in India, they're working on this problem statement, right? And they have 1,000 atom molecule that they're trying to simulate using HPC systems. Now they are thinking of moving this entire problem statement to quantum so that they can solve this fast. So that's the attempt that they're making, sir.
Sir, is it that NP hard problem because of size of the problem, or in the laboratory level can we reduce that? Every problem you have to consider as NP hard.
Yeah. That is again NP hard. Sometime becomes NP also actually, depending upon the compute power that is available. But some problems cannot be reduced, sir. So those are problems.
Prototype level also it won't come.
In prototypes, today these computers are not stable actually. So we need we need very stable environment to solve these problems. These quantum computers are still not so stable. So we can solve small size of problems, not very big problems like the portfolio optimization problem I spoke about. Got about 40 qubits. We can run it on a simulator, or we can actually run it on a small size quantum computer also. But bigger problems are still little infancy. So we waiting for bigger quantum machines to come. And once they come, so we can solve this big size problems. So today's problems will appear very small for commercial activity. So that's why, so that gap is there. So even our customers say, okay, so the problem that you are solving today, I can solve in some form in classical computer, but not on quantum computer. Right. So there is that inflection point should be reached, sir. So once we have 1,000 plus qubits, we'll reach that state. and that's when the classical computers can never match quantum. So waiting for that kind of opportunist moment. Even with that 156 qubit that IBM has today, so we'll not be able to solve the problems that that computer can solve on classical computers.
Sir, good evening,
thank
sir. This is Professor Balakrishna,
Sir,
Director, JNT Kakinada. I am audible, sir?
Yes,
sir, you
sir.
are audible, sir. Sir, but we are running short of time as the
Yeah.
second resource person is also on the line, and he has another engagement. Kindly, we can interact him personally.
Okay.
Sir, kindly, we can give time to second resource person. Thank you very much, sir, Sridhar sir, for your wonderful presentation. Definitely, we will interact with you for all the queries which vice chancellors and directors are raising. And now I may request Dr. L. Venkat Subramanyam garu, the IBM Quantum India lead, and welcome you, sir. Am I audible, sir?
Thank you, sir. Yes, sir, I can hear you. Are you able to hear me, sir?
Yeah, you are welcome, sir. Please.
Thank you so much.
Sir, just give me a minute, sir. I would like to introduce you to the audience. Here, sir, all the vice chancellors of across AP and deans, academic, and some principals are all present. And it is also live streaming YouTube for faculty as well as students. Sir, Dr. L. Venkat Subramanyam garu, the IBM Quantum India lead, and his PhD from Delhi. He is recognized as an IBM master inventor. He has been granted 38 patents and has published over 150 research papers with over 3,300 citations. Recently, his book Quantum Nation hit the bestseller list in India and on Amazon. The Quantum Nation explores the journey of quantum computing in India, highlighting key developments, the impact on technology and society, and how India is contributing to the global quantum computing landscape. From independence in 1947 to the technological marvels up to 2047, Dr. Venkat Subramanyam takes us on an extraordinary journey through India's evolution, weaving together history, personal experiences, and groundbreaking advancements. He highlights how visions, milestones, and structural roadmaps have shaped our nation's progress. So he is actually a great speaker and also is recognized as a TED speaker. Recently, IBM Master Inventor talk is also hit the YouTube. With these few words, I welcome you, sir. Please move on to your presentation. Thank you.
Thank you, sir. It's such an honor to be in front of all of you. I'm really grateful for this opportunity to talk to you on World Quantum Day. So I'm going to give you an overview of where quantum is and how quantum is evolving. So today on our laptops, our mobile phones, or any desktop, this leftmost thing here, this is how we interact with a computer. You write a program which is in Java, C, C++, any language. That program then gets converted into machine code. And today the machine code for our classical computers, which is our laptop, our mobile phone, all of these, is basically it is zeros and ones. The fundamental unit of computation today is zeros and ones. On a quantum computer, you can write using the same higher level language, which is Python. But what is different is that the compiler or the transpiler no longer converts it into zeros and ones, but it converts it into a new set of code, which is basically qubit compliant, where it goes beyond zeros and ones. And that's where the special power of quantum computing comes in from, where quantum computers go beyond the zeros and ones which are there. But the interaction with the computer itself does not change. It is the same higher level language, Python, you can use to program your quantum computer. So in that sense, quantum computing is very easy for anybody today, any student, any developer. It is very easy for them because just like today's computer, they can program it using the same But then, so this used to be the most powerful supercomputer in the world, Moore's law. You all know Moore's law. Every almost 18 months, compute power doubles. What does that mean? The mobile phone that you have or the laptop that you have becomes, becomes more powerful. Every few years, your mobile phone is having a better camera. It is having better processing power. You can run better games, more powerful applications can be run. And this is primarily because of Moore's law. Moore's law is doubling. For several decades now, it has been doubling the power of our compute. But then even this compute is not enough when you come to, for example, doing certain tasks like simulating molecules. A molecule, a simple molecule like caffeine. Caffeine is one of the small molecules of nature. If we try to simulate the caffeine molecule on a classical computer, it will take 10 to the power 48 bits. 10 to the power 48 bits is equal to 1/10 the total number of atoms present on Earth. Are we ever going to build a supercomputer this big? It's very unlikely that we will ever build a supercomputer of this size. And hence, this is one problem, molecular simulation, which is key in pharmaceuticals, better drugs, better medicines, better battery materials, better fertilizers, better, ISRO launches satellites and, rockets, better rocket fuel, better materials to build the rockets. All of this requires molecular simulation, and this is something we cannot do on a classical computer precisely because of this, because we are not able to simulate even for a single instant what a molecule is doing. But that's where the quantum computer comes in. With just 160 qubits, the quantum computer can simulate the caffeine molecule. Okay, so something which is impossible on a classical computer can be done on a quantum computer, which is molecular simulation. Another example, today all our cryptography, all our secure communications, all this, the Zoom call that I'm doing, the communications you do on online transactions with banks, the UPI transactions which you do, all of this is based on one very simple fact, that you cannot find the prime factors of a large number. What are prime factors? Prime factor of 15, 3 into 5. 3 is indivisible by any other number, 5 is indivisible by any other number. So 3 into 5 are the prime factors of 15. Prime factor of 49 is 7 into 7. But what is the prime factor of 1, 2, 6, 9, 8, 7, 3, 2, 1, 5? A very long number, a 2048 bit integer. The prime factorization of that number takes 8 billion with a B years on a supercomputer. So hence we use this fact to do all our encryption today. All our encryption is based on the fact that you cannot break a large prime number. So I take, when I do a transaction with the bank, I create a large prime number, the bank creates a large prime number, they multiply, put it there as the key. And that cannot be broken. And hence all our communication is based on this simple fact that prime factorization will take 8 billion years on a simple supercomputer. But the same thing, it was shown that it can be done in a few hours. In fact, 8 hours, you can run this on a classical computer. Sorry, just 1 minute. Okay, just 1 minute. I'm sorry. Yeah, I'm sorry. Okay, I hope I'm visible and audible. Yes. So on a quantum computer, there are two problems which I just showed you. The first problem is that you cannot do prime factorization in any reasonable amount of time. The second problem, which I told you, is that molecular simulation, which is important for making medicines, which is important for fertilizers, all of these cannot be done on a classical computer. It can only be done on a quantum computer. And hence, and Sridhar sir also mentioned, this whole problem of encryption means that we have to now move to new encryption techniques which are quantum safe. So this is, and the whole point now is what is the reason for this? The simple reason is that classical computers use zeros and ones for computation, and that is not good enough for simulating anything in nature. Okay, nature goes beyond binary; it goes to other complex, numbers, and hence the zeros and ones which our today's classical computers use is not sufficient for computing several things. And that's where the quantum computer comes in with its qubit. The qubit has some very special properties. Number one is superposition, where the qubit can be in both 0 and 1 state simultaneously. The second big property is that two qubits can be entangled. So think of it like I have a coin. If I flip it when it is in the air, it is both heads and tails. It is neither heads nor tails, but both simultaneously. Same way, qubit can be both 0, both 1, okay, at the same time. The second is I have a coin, you have a coin in your room, wherever you are at this point. If our coins are entangled, then by looking at my coin, I can say exactly what your coin did, which means that two or more qubits can be entangled and made to behave in special ways where all of them are simultaneously connected. And this is where the special power of compute for quantum computers comes in, where they are able to use these properties to do things like molecular simulation, which cannot be done on a classical computer. Do things like prime factorization, which is the basis for all our encryption today, which can be done only in 8 billion years. On a classical computer can be done within a few hours. And so what this means is that quantum computers can solve certain big problems. And that is the reason why 34 countries, more than any other technology, today 34 countries have national quantum missions of their own. The year 2025 has been declared the year of quantum by the United Nations. And countries, their advisors, their security agencies, their scientists are all telling countries that the country that takes full advantage of quantum and takes the lead will have economic dominance over Earth for several decades. And that's the reason why India and 33 other countries, US, China, Japan, South Korea, Australia, all of them have national quantum missions where each country is trying to get ahead of everybody else. Okay, that's the very important goal that people are now working with at this point of time. But classical computers are not going to go away. One simple operation, multiplication, which is the basic operation for computing, is hundreds of times faster on a classical computer compared to the quantum computer. And so the future is going to be CPUs, GPUs, and QPUs working together. So even today on your laptop, you only have CPU. When you want to run an AI program, you then go on the cloud and run your AI program. Okay, that's how we work AI today. And in the coming future, what is going to happen is we are not only going to run AI, but we are also going to run cloud on the cloud. Quantum on the cloud. So that depending on the problem, we are going to break it up into different parts, into different pieces. Some part runs on the CPU, some part runs on the GPU. and then some part runs on the QPU to be able to then solve unsolvable problems. Okay, that's the whole goal of quantum computing, to solve things that you cannot solve using any other compute at this point of time. I'm sorry, is there too much noise? There is noise in the background. I hope it is okay. Are you able to hear me?
Yes, sir. Audible.
It's
Very much.
very clear.
Okay, okay.
It's very
Very good.
clear.
It's
Okay,
clear,
sir.
sir.
Thank you, sir. Okay, so that's the reason why people are now using all the three together. And for the first time in the history of computing, computing has branched. There are now two types of computers. One is your mobile phone, laptop, supercomputer, which has the fundamental unit of information as zeros and ones. That's one type of computer. The second branch of computing, which is very different, it is got nothing to do with zeros and ones, is your quantum computer, which uses qubits and which uses, as I said, these special quantum mechanical properties to do the computation. So for the first time in history now, computing has branched completely into two types of computers, one using zeros and ones, and the other using quantum mechanical properties of superposition, entanglement, and interference. And this now also, I talked about Moore's law, which you all know, which says that every 18 months, compute power doubles. Okay, that's what has been happening for several decades. And that's why, our children come and say, can I buy a new mobile phone? Because the new mobile phone every 2 years is doubling in its capacity in terms of what it can do, in terms of the camera and everything else. And we are seeing similar progression in quantum. 2016, the first quantum computers from IBM on the cloud were 5 qubits. 2024, IBM released the 156 qubit quantum computer. And by 2033, it will reach about 1 lakh. Okay, so you're seeing the same exponential growth in the power of quantum computers at this point of time. And which means that, quantum computers are very, very quickly advancing. They are very, very fast in their evolution. And we are seeing new and new things being able to do on these quantum computers. Now, one very important, aspect of quantum computing is the term called quantum advantage. What is quantum advantage? You have your classical computers today, which can solve certain problems. The day quantum computers surpass these classical computers, they can do better than these classical computers on real business or real scientific tasks, which can be anything. It can be you running the factorization algorithm. It can be a student running the molecular simulation experiment. All of that using today's quantum computer, if we are able to do something much faster, much more effectively, much more efficiently on a quantum computer, that is called quantum advantage. When are we going to reach quantum advantage? IBM has said we will reach quantum advantage next year, 2026. In the next 1.5 years to 2 years, we are going to see quantum computers solve problems which a classical computer can never, ever, ever solve. Okay. Now the question is, who is going to solve this? Which country is going to be the one which achieves quantum advantage first? So take an example, internet. Internet came in the year 1983. Internet sat in the lab until Netscape came with a browser. Before that, nobody knew how to go to a website. Can you imagine internet without your browser? How will you go to websites? Nobody knows how to go to websites. The first innovation in internet came in the late 90s. For over a decade, internet was sitting in the lab. After Netscape came, and then Google came and said, okay, there's all this data on the internet. How do we search out the things that are relevant to us? Before these two, internet was sitting in the lab. Same, AI. AI came several decades ago, but until OpenAI came and showed that you can use AI for doing question answering, for answering your queries, until then, AI was sitting in the lab. Same way, quantum today is sitting in the lab. Somebody has to come and show quantum advantage, and that's when we are going to realize the full potential of quantum. And who is going to achieve quantum advantage is the big question. And the answer to that is it has to be India. India has to achieve quantum advantage. Why? I will give you some facts and figures. Quantum systems from IBM today are freely available on the cloud. Who are the maximum users of these systems? Indians from India. Not Indians from US or Japan or wherever, but Indians sitting from India are the biggest users of the quantum computers available in the IBM system today. This is a McKinsey report which says the number of graduates in quantum technology is the highest in a single country. India is the highest. Okay, India has the highest talent. European Union is the collection of several countries. Okay, so if India has the maximum talent, then who is going to bring quantum advantage? It has to be India. It has to be India. And that is the reason why, National Quantum Mission was announced by Government of India, Department of Science and Technology. Sridhar sir already told you about this. But the goal here is to realize the potential of India. We have the talent, we have the young people, we have the largest number of software developers at this point. So why should quantum advantage come out of anywhere else? It has to come from India. And this is the vision of Quantum Valley Amaravati also, which was stated by the Honorable Chief Minister, Chandrababu Naidu sir. The goal here is to provide the incentives, provide the capabilities, provide the infrastructure so that the youngsters who are already world beaters today, they can then come in and start using these quantum computers and solve real problems which are of importance to India. Let us call it, let it be agriculture, let it be energy, let it be climate change, water, all our rivers are getting polluted. How do we change all of that, come up with new materials which can clean these rivers? And all of this, remember, is molecular simulation. It is about doing optimization. It is about doing mathematical problem solving. And compute is the major driver today for any technological advancement, for economic development. And that's why I also told you that 34 countries today have national quantum missions because they want to be the first to take advantage of this. They want to be the first to build an economy out of this. Today, your laptop, 5 countries control the supply chain for it. China, Japan, South Korea, Taiwan, and US, 5 countries. Any compute you look at, whether it's a mobile phone, it is your laptop or a supercomputer, 5 countries have controlled the entire supply chain for your any electronics today, most of the electronics, most of the computers. But the future is going to be quantum, and India has to be one of those countries. Whoever is going to be controlling the supply chain for quantum computing, India has to be in there. And that's the reason why the National Quantum Mission has come up. And that's the reason why Andhra Pradesh is looking at building a quantum valley, surpassing Silicon Valley. Silicon Valley, as you know, is in California. The goal here is how do we build a quantum valley in India, which is the future, which is going to be the driver for all of the future technologies, because the power of quantum computing is immense. And that power, as I said, quantum advantage is going to be seen very soon. It's not very far away. Next year, people are talking quantum advantage. Next year, using the existing quantum computers. And this is just the beginning of quantum computing. Remember that. So as the future dawns on us, this is our big opportunity to take the lead. And that is the whole reason and the purpose that the National Quantum Mission has been, set up. That's the reason why the talent of India, this time the goal is, we have always been great at building talent, whether it is semiconductors, AI, computing, any of that. Father of Pentium chip, Vinod Dham, Indian. Father of fiber optics, Kapani, Indian. We have never fallen short in terms of finding talent, but the challenge has been this talent has always had to fly away, fly out of India to go and build their careers. This time, the goal of the National Quantum Mission and visionaries like the Honorable Chief Minister of Andhra Pradesh is to build the quantum valley here so that our talent can find careers in India and they can build that career and solve problems out of India for the world. Okay. Now, the National Quantum Mission has also looked at building, minor programs, new courses, which were just announced, the AICTE, DST announcement on undergraduate courses in quantum technologies, where students, mechanical, civil, whatever their branch, they can all take these 6 courses and then they can get a minor degree in quantum technologies in addition to whatever other degree that they are getting. Okay. So these are all things which the government is doing. In fact, there is also a national startup program which is for quantum. So they are funding startups to the tune of 1 crore to 25 crores. Youngsters have already 8 startups have been funded under this. Many more will be funded. The goal again is to make sure that Indian startups succeed, able to go and. So today, quantum computers are freely available on the cloud. You just type IBM Quantum, you will be taken to this website, where you can sign in and start using a quantum computer right now. So on World Quantum Day, please check this out. Please see how you might want to use a quantum computer. As I told you, India is already one of the power users of these quantum computers. Our children from second tier, third tier cities and towns and villages are already using quantum computers today. Okay. So there is a huge grassroots level, thing which is happening in India already. And so this is another opportunity to widen the again for free. And many colleges have already started using these to train and teach their students. Jobs. My team is already hiring in India, BTechs, MTechs, PhDs, everybody, and even MSc and all of that for quantum computing. And we are not the only people hiring. There are hiring TCS, Infosys, LTI Mindtree, and also the National Quantum Mission. All the IITs have been given extra funding just for quantum, and they are also now using these funds in Andhra Pradesh, the ISER, IIT, also in Amaravati, some of the private colleges like SRM and Amrita and others are already building teams, in quantum to train their students and to take some funding which the National Quantum Mission is providing. Now, already people have started looking at use cases from areas ranging from banking to automotive to chemicals, life sciences. UPI, I'm sure UPI is the biggest platform for transactions today in the world, by far the biggest. To put together China, US, Europe, everybody, you put them together, they still don't add up to UPI. But there is a big problem in UPI. UPI, 99.9% Indians are honest, but 0.01% are conducting fraud. But as UPI becomes bigger every second, millions of transactions, how do you find these fraud use cases? For the best supercomputers, it is impossible today. They cannot find it in real time. The hope is that quantum computers will be able to find these fraud use cases. So as UPI grows, the number of fraud, the 0.01% also becomes larger and larger in transaction value and numbers. So that's just one example, fraud monitoring. But there are, as I told you, molecular simulation, you can't do it on a classical computer. So quantum discovery of efficient drugs, clinical trials. So across the board, several industries are going to get, impacted by this. Already there are many airlines we are talking to, which are looking at how do they, optimize their flights, their number of aircraft, the number of pilots are fixed, and they cover, let's say, 40 towns in India. So how do they do it more efficiently? How do they do it more cost effectively? So all these are examples of problems which quantum computers are expected to solve. And that's where, the whole advantage comes from. Is there a question, sir? Okay. Yeah. So there are already, and today, the three main types of problems that quantum computers are good at solving are, one is simulating nature. Molecular simulation is an example. The second is mathematics and processing data with complex structure. So we are all using AI today. Okay, we all know AI. We are using ChatGPT and others, but there is a big problem with AI. I call it the cat problem. When you were a child, how many cats did you have to see before you recognized a cat? Maybe one, maybe two. The first time your mother showed you a cat, you said, "Mama, cat." But for a computer today, for an AI program, one cat is not enough. It has to see thousands of cats. Thousands, okay. Cat from this angle, cat from this angle, cat, black cat, white cat, cat occluded cat. All sorts of cats have to be seen by AI. Before the same cat, that you need only one example. You just need one example. Your child needs one example. That same requires thousands of examples in today's AI. And what does that mean? That means that an LLM, which comes up today, on this side, an LLM comes up. On the other side, what comes up? A power station comes up. And that's why many of the tech companies are now in the process of purchasing nuclear power plants. And the whole problem there is that AI of today is not efficient. It is not able to, take the data and build models on top of that data efficiently or effectively as our brain is able to. And that's one of the big problems of AI today. And that's mathematics and processing data with complex structure. So the whole goal here is that quantum computers are expected to solve some of these problems. And, the AI problem that we are observing, maybe we will bring it closer and closer to looking at fewer examples to train your AI models, which means less power, which means lesser time, and all of that. And the third is search and optimization. And these problems are being applied across areas like automotive, financial services, high-tech industry, and several companies, like Sridhar sir just told you that they have been already working in these areas for 7 years now in India. There are other companies like LTI Mindtree and others who are also working on quantum computing in India for several years now. And hence we are all set to go and solve some of these problems. And as I told you, in National Quantum Mission and the Quantum Valley that is being
Sir, you're not audible, sir.
Sir, for the past few minutes, he is getting an alarm. Low battery, low battery, low battery. Maybe
Oh.
that's the problem.
Okay, okay.
Not observed that.
Okay, okay. I will get that.
Yeah, I'm so sorry. Actually, I just landed in Ayodhya, and that's my laptop ran out of battery. So the goal here is to make sure that, quantum has so much advantage in terms of the problems that it can solve. And the goal that we have now is to utilize this power of the quantum computer to solve problems of importance to India and the world, and to solve them right out of here in India. I don't know, are my slides being projected, sir? If you can project them, if that is possible.
Yes, sir. We'll try.
I'm sorry. Yes.
Yeah, we'll do that.
అది ఆన్ చేయలేదా?
Sir, meanwhile, we can go to some questions if there are from anybody in the audience. We can take questions to save time. Sorry about this.
Sir, can I ask you, sir? I am Professor
Yes, sir.
CCC,
Please go ahead.
Amaravati College of Engineering Principal, sir, Professor of Electronics and Communication. Sir, my question is related to the uh, QPU, sir. In future, QPU, will they replace this TPU, sir? Today's
So,
quantum AI systems are usually hybrid, sir. The main problem with the quantum hardware is still highly error prone, that we all know. And the qubits are highly fragile and lose information very quickly, sir, which is making them which is making the training unstable and unreliable also, sir. So in future, can we expect this hybrid quantum computers for only doing the today's means quantum AI system?
yes, sir, that's an excellent question. So the question is about the QPU or the qubits which are there in the QPU. So the you think of a, yes, sir. Sorry, did you have a further question?
Means can we expect QNN and QML in full-fledged manner in place of this CPU, GPU, and TPUs?
Yes, sir. So the QPU today, as sir pointed out, are very noisy. Okay, they have lot of noise in them, and which means that any computation which you run is of limited computation only can be run today on your QPUs. Okay, so but think about the computer, today's computer. The computer error corrected bits came only in 1950. Okay. Before 1950, the computer was used in World War for breaking code. It was also used in the nuclear, conducting the nuclear experiments. The same unstable bits. Bits were unstable before 1950. Okay. But they were used in World War. They were also used in, the nuclear experiments which were conducted. And so for the same, in quantum also, we are seeing that even before stable qubits are there, we are going to observe quantum advantage. As I said, quantum advantage will happen next year. Before stable qubits are there, stable qubits are only expected in the year 2029, 4 years from now. Okay. But before those 4 years, we are going to see quantum advantage. That's what is expected. So yes, sir, qubits are not very stable at this point, but that has not stopped the scientists from showing that these qubits are useful, and they have been shown to be useful for molecular simulation. They have been shown to be useful even for AI problems. So the same cat problem which I told you, we are observing that if we use quantum there, we are able to not require thousands, but we are able to require just a few hundred. Okay. So there is already a scaling in terms of what the quantum processor of today, okay, today. And remember Moore's law, doubling every year, every 2 years, that doubling will also happen. So we should not wait for perfect qubits before we start solving problems. And nobody is also waiting for perfect qubits. The world is moving. And as I said, we need to be the first people to show quantum advantage out of India.
Right now, this real world AI workloads are still out of reach. But in future, we can expect them as a general purpose, practical general purpose. We can use them.
Yes, sir. Actually, today itself you can use QPUs. They are available over the cloud. So the QPUs are already there. Okay, so Microsoft showed some experiments, Google showed something. IBM has also shown that you can do certain molecular simulations using the QPU. So the QPUs exist. In fact, from India, the slides, if somebody shows, IIT Madras has already shown protein folding using the current QPUs which are there over the cloud. Okay, so that compute already exists. Okay, so we don't have to wait for any special more qubits. It is already there, and that can be used. And in India, already TCS is using it, IBM is using, IIT Madras is using, ICER, Tirupati team is also using that. So many people in India are already accessing these qubits over the cloud and trying to solve some of these problems like protein folding, which is an important aspect of drug discovery.
Thank you, sir.
Sir, good afternoon, sir. Am I audible?
Yes, sir. Yes, sir.
I'm the professor of computer science, JIT Calcutta, Krishna, and also I was a manager in TCS, but I came back from TCS. Actually,
Yes,
my
sir.
question is, we have a lot of research scholars. So now all our research is on artificial intelligence, machine learning. Now we are bringing the new technology, that is quantum computing. So what is your advice to all the research scholars, and how we have to go into the quantum computing, and how we can proceed our research? Can you guide us?
Yes, sir. This is excellent question. Okay, because AI is today's technology, quantum is tomorrow's technology. Okay, so even though a lot of hiring is happening, a lot of potential is there, but today the industry is using AI. Okay, all the jobs are in AI. 99% jobs are in AI, 1% is in quantum. Okay, now the AI people, the AI research scholars and all, I think they need to build systems today, AI systems. Okay, so whether it is building an LLM for India, we still don't have an LLM for India, and a homegrown LLM we don't have. These are real problems which people can solve. And in fact, AI, for years we've been saying, oh, India has so many languages. Somebody from Andhra only speaks, Telugu. Somebody from Tamil Nadu only speaks Tamil. Somebody from Delhi only speaks Hindi. Then how do we do integration? AI is that integrator now. In 2-3 years, it does not matter what language you know or don't know. AI will solve that problem for you. You can sit here. If you only know Telugu, you can still solve the problems of somebody in Korea who only knows Korean. Okay. AI will solve that problem, and it will open huge opportunities for us in India. Now, for the research scholars, what we tell them is that keep doing the AI that you are doing, but try to solve that same problem using the quantum processor. Okay. Because quantum processors are there. Try and solve that using quantum. And what we are seeing is that as soon as that student starts using quantum, now they're trying to compete. AI versus quantum, AI versus quantum. Okay. And what we are seeing is that same student's AI also becomes better, because that student now thinks from a different angle, from a different perspective. The cat problem, which I told you.
Quantum is very good at solving, this whole problem of, thousands of cats versus one cat that we humans require. We are seeing quantum can address that. But even if the student is not able to solve that cat problem completely, we are seeing that they are able to get closer to the human processing because they are able to think deeper, even in the classical AI. Look at DeepSeek. What did DeepSeek do from China? They took the same OpenAI model, they put it under reinforcement, learning, and they showed that you require 20% less resources. I'm sorry. In fact, 20 times less resources. Okay, not 20%, 20 times, factor of 20. Okay, that is the level of thinking which you can drive by making people solve problems using a combination of quantum and AI, because that thinking itself changes. You're thinking in one direction when you're thinking only AI, but as soon as you bring in quantum, that helps you add a new perspective. And we are seeing this across India, that when students start learning quantum, they get better in classical also. They are able to do better AI, they're able to do better optimization, they're able to do better data science. So their thinking itself broadens and it helps. And that's why I think one of the focus of AICTE and DST has also been to introduce just 6 courses. In BTech, I think there are at least 60, 70 courses that our children do, right? Out of that, we are saying only just to do 6 courses in quantum, and that's going to broaden your perspective, whether it is civil, mechanical, physics, chemistry, maths, computer science, electrical engineering, whatever your engineering field, because the future is not just AI or it is not just quantum. It is about taking a domain like construction, or a domain like pharmaceuticals, a domain like automotive, and using the power of quantum and AI to solve and accelerate things there. That's what the future is. Until past 10, 20 years, you could just be a good programmer and get away with it. Now programming is done by AI. You don't need people to do programming. And hence, what does the human need to do? The human needs to become the domain expert in construction, the domain expert in bridges, the domain expert in automotive, so that they are able to use that coding power which the AI is doing now. It is writing programs, to use that on quantum and on AI to solve problems of humanity like drug discovery and all of that. So I think, like Sridhar sir was saying, things have become very interdisciplinary. I think what has happened is every discipline now has 2 tools in their hands, AI and quantum. Now it's for you to decide how you want to use that tool to further make progress in the domain that you are working in.
Sir, is it visible for you? The presentation is shared now.
Yes, sir. Yes, sir. Thank you. So, yes, so we can move on. So the next slide, we can keep going.
Thank you so much, sir. You have given very nice explanation, and we have taken a long time to clear our doubts. Very thankful. So it is
Thank you.
useful for research scholars of in Andhra Pradesh.
Yes, sir. And sir, one more thing on the education part. Okay, so we are very keen that we work with your students also to give them that industry perspective. Many people keep saying that India produces lot of students, but sometimes they are not fully industry trained. So our goal now is to make sure that, when you are in college itself, can that student get some industry perspective? Can that student start looking at problem solving? Because today, industry is looking for students who are hands-on, who can build things, whether it is using software or whether it is using hardware. Students have to build things. Okay, so that perspective, if we can bring in their PhD program, MTech program, or even BTech in their final year, if they can do some real projects, because think about it, an LLM, which has become so powerful today, we don't have LLMs in our Indian languages. Can these be the student projects? And we are very happy to help your students think about doing these kind of problems where the data can be your local, let us say your Telugu language book, your 10th class books, all the books loaded into an LLM for the students, and the student can ask any question that they want, and the figure comes out and the answer also comes out. Think about the power of this, how we can enable all our students. And these are, I think, the kind of projects that our BTech, MTech, and PhD students need to be driving, which are real life problem solving for, things that we need to solve. So, sir, it's 2 o'clock. I don't know how much longer we can go, but maybe we can just take any questions which are there. And
Sir, I have one
yes.
question.
Yes, sir.
Now the government is going to spend Quantum Valley. If still we are learning how to take a problems readily, that we have to go side and learning is another part. Can you give some suggestion on that?
Krishna University VC. Ramji and Ambedkar University VC చేశారు.
Yes, sir. Yes,
Is it
sir.
audible, sir?
Yes, sir. I heard the question.
Yeah,
And
understand.
yes, sir. And this is an important question for the whole country, sir, because we want to learn. Of course, everybody wants to learn. But at the same time, we want to create career paths for the people who are learning. There's no point just learning and then do what with that learning, right?
My point is, sir, here Amaravati going to spend 3-4 years around 30% of the state budget. Now readily to tap that resource or tap that fruit and involve academia in that particular business. How best we move? That's my intention.
Yes, sir. Yes, sir. Yes, sir. And in fact, a lot of this, investment is actually coming from industry today. Okay, sir. So the state is going to, I hope what the state does is to enable the academic institutions, for example, funding the faculty, funding the students, to work with the industry which is going to come to Amaravati. Because if Amaravati does not have industry, there's no point, right? It has to have industry. And I think that's where the Honorable Chief Minister's goal of inviting IBM, of inviting TCS, of inviting, L&T to come and put their money, to invest their money, and build industry and, projects there. And the goal here will be for academic institutions like yours to come and work with this industry to to see how their problems can be solved. So for example, if pharmaceutical industry comes to Amaravati and they are looking at drug discovery and they're trying to see how medicines can be made faster, then I think the academic institutions in Andhra Pradesh should have these as the projects to work with the pharma industry which comes to Amaravati, to take problem statements from them, to say that, okay, what are the important problems for you? And we will have these as the projects for our students.
Okay, sir. Thank you.
Thank you, sir.
As time is running short, can I hold down all the your presentation?
Yes, sir.
No, just I hold down all the slides. Yeah,
Uh, thank you, sir. So, anything else?
Just I want to hold down all the slides for viewers' benefit. Are the slides are visible, sir?
Yes, sir. Yes, sir. So I was saying that we can stop with the slides because anyway, it's 2:05 now.
Okay.
So maybe we can just take any other questions which are there, because in the slides, I was just going to look at more examples of what industry today is doing and which could be potential examples of what academic institutions can work on. But as I told you broadly, these are in different areas, so you can look at any problem where you are using AI or data science or even automotive or anything, and look at quantum as a tool to try and solve those problems.
Excuse me, sir.
Yes, sir.
Yeah, I am Professor Munswami from Department of Statistics, Andhra University. Yeah. So,
Yes, sir.
yes, sir. Sir, mathematics and statistics plays a fundamental roles in the development and implementation of quantum techniques. But what are the basic tools and techniques required for quantum computing to teach?
Yes, sir. That's an excellent question. And in fact, those 6 courses prescribed by AICTE basically go into this, what you just asked, which is that question. And the answer to that is very simple. Linear algebra is what we expect from the students. Linear algebra, matrices, linear equations, linear algebra. That's all the basic requirement. And this course can actually start in the first year itself. Okay. So the 6 courses cover the basics of linear algebra. That's number 1. Number 2, it covers the basics of programming, and then it slowly introduces the concepts of quantum mechanics. Okay, sir. So we try to keep it as simple as possible for the children so that they can start in first year itself and they don't feel scared or anything. And they start solving real problems using simple linear algebra and basic programming. So that which is required in the initial stages.
Sir, what about the probability distribution, sir?
Yes, sir, probability is also required, but we slowly bring that in a bit later. So in fact, sir, we started this in NPTEL, okay? In NPTEL, 15,000 students registered. And out of those 15,000, 7,500 were 12th class students. Okay. So we could not go very deep into anything there. But we introduced basic, slowly, different concepts, and the students stayed with us. They didn't drop out or anything. So we try and start very simple with linear algebra, matrices, linear equations, basic programming, and then slowly, as you said, bring in probability and statistics, quantum mechanics, all those theory. Because as you know, sir, even Einstein never believed in quantum mechanics. So even he said it's, I don't agree with this, right? In his whole lifetime, he never agreed to quantum mechanics. But he asked so many tough questions that other scientists spent a lifetime solving them. And today we have, quantum computers.
Thank you, sir. Thank you very much on behalf of APSCHE, Amaravati, and on behalf of all the universities. Thank you very much, sir. You spent a lot of time in the schedule at Ayodhya. Really.
Yes, sir. Yeah, I've come for darshan today, sir, and I'm sorry I'm outside and talking to you, but I hope I was clear and you could hear my, talk. But we really want to work closely with you and make sure Andhra succeeds and builds a quantum valley.
Sir.
Yes, sir. Thank you.
Thank you. I thank all the universities, vice chancellors, deans, and principals for joining us. Thank you very much.
Thank you, sir. Thank you.
We will be in touch with you.
Yes,
for,
sir.
Different assignments like curriculum design, trainings, internship. Thank you, sir.
Yes, sir.
Thank you.
Bye, sir. Thank you so much.
I also thank Sridhar Garu from TCS, Subramanyam Garu from IBM, and also JBB Reddy Garu from DST. Thank you very much for all your support. All the vice chancellors, deans.
Thank you, sir. Bye-bye.
Thank you.
Thank you.
Thank you. Thank you very much.
I request all the principals and teachers to subscribe this YouTube, sir. This is available in this YouTube link. Now we are closing this. Thank you.
Thank you.